So what is mass spectrometry? So there's a couple of different metaphors that we use to describe what we do with mass spectrometry. Specifically, mass spectrometers are instruments that measure the masses of individual molecules that have been converted to ions, that is, they're ionized. So we have a scale here. So nominally what we're doing is weighing a molecule. So something has a specific weight that is a characteristic of the molecule or compound, and we're weighing it essentially. However, since something is so small, or only a few atoms or compounds, it's too small to use gravity to weigh, so we have to ionize it, and then we can use electrical and magnetic fields to manipulate it and then determine the mass to charge ratio. Another analogy that people like to show when describing what mass spectrometry is capable of is this puzzle analogy, in which you can weigh the entire puzzle and then you can also break it apart and look at the individual pieces and how the pieces go together. And this is essentially what we're doing in MS/MS, or tandem mass spectrometry, which we'll get into later in this lecture. A brief history of mass spectrometry. It arose in the late 1800s with J.J. Thomson and his study of cathode rays. And at the top right of this slide, you can see one of the earliest results from a mass spectrometer, in which they identify isotopes of neon. So they have neon 20 and neon 22, and they're just changed in their parabolas by their molecular weight. One of J.J. Thomson's students, Francis Aston, went on to develop mass spectrometers further using electrical and magnetic fields to both accelerate and then to deflect the charged particles. And here on the bottom right is one of these very early mass spectrometers where you can see the tube full of gas and just some really incredible magnets and electrical fields that they used to manipulate these ions. It's resulted in a number of Nobel Prizes for mass spectrometry and related science. So in 1906, Thomson won the Nobel for conduction of electricity by gases. In 1922, Aston for the discovery of isotopes. 1930, Lawrence for a cyclotron. And in 2002, Fenn and Tanaka for their soft absorption ionization techniques. So before we get into any further what a mass spec does, we need to talk about elements and isotopes. So an element can be defined by its mass, and that's been known for ages. But one of the reasons that Aston won the Nobel Prize was for his identification of isotopes, which are elements which have the same number of protons and electrons, but a different number of neutrons, which changes their overall mass. So here is an example where we can use instruments that resolve the isotopes to allow us to correctly measure exact and monoisotopic masses. So for carbon, carbon-12 is the most prevalent isotope, but carbon-13 also exists in nature, and you can see this in large molecules. And we have to take that into account when we're calculating the mass and the exact mass that we're looking for in the mass spectrometer.
Emma?
Emma,
yeah. Could you go back one slide?
Yep.
So something in this that I think is important to make note of is that when you have a biological molecule, so most amino acids, if you look at them, they actually have numerous carbons. So, and if at a 1% rate, as long as you have 100 carbons in a molecule that you're measuring, then the most abundant peak is actually going to be that second peak, if you want to point at that, Emma, the carbon-13 peak. And so when we work with biological molecules, if you then get to 200 carbons, you're going to be in that third peak, and so on and so forth. So the larger the molecule, then the more skewed you're going to have this, this isotope ratio. So this becomes really a key thing when we're measuring biological molecules. And a lot of the software that is made in the mass spectrometer, a lot of the additions in the last 5 to 10 years have really been focused on how to isolate specifically the masses that have carbon-12. So you can think about why that might be important. So why would you only want carbon-12 and not carbon-13?
So moving on is just a schematic here of an example mass spectrometer and some workflow information where you have some sort of sample preparation or separation ionization, ion selection, ion detection, and then data analysis. And so that loosely lines up with this example of a Thermo Fisher instrument that we use down in the core, where we have a liquid chromatography set up prior to the mass spectrometer is under high vacuum, and you have a source of some sort, which we'll talk about, ion optics, ion analyzers, and detection, and then the computer and entire system that we use to do the data analysis of the output raw files from the mass spectrometer. And I included this YouTube video. We're not going to watch it right now, but if you click on it, it's a pretty in-depth view of what the ions are doing in this Orbitrap mass spectrometer, and has some really jazzy dance music behind it. So I encourage you to check that out later.